Hello, my name is Nian. In this talk, I will introduce our work on solving the challenges faced by neural radiance fields in virtual reality. We presented a novel model incorporating the human psychophysics of visual and stereo acuity into an egocentric neural representation of 3D scenes, which enables high perceptual quality and low latency VR viewing. VR is becoming ubiquitous with the rise of displays and platforms. Practical VR systems require high quality, low latency, and egocentric viewing with high resolution, large field of view, and stereo displays. These requirements are fundamental to ensure realism, comfort, and safety. The recent advancement of neural radiance field methods has demonstrated the photorealistic quality and continuous view changes of 3D scenes. The high quality and flexibility show promising applications for future VR content creation and consumption. Because of its great potential, NeRF has drawn extensive attention. Many works were proposed to extend its ability, generalize its representation, and optimize its rendering performance. However, when applying to high-resolution, stereoscopic, and egocentric viewing, the heavy computation of inference makes NeRF high latency and low quality. This not only harms the experience but also causes sickness. To tackle these problems, we propose the first case constant neural rendering for VR. We first represent 3D radiance fields with our egocentric neural representation. The tailored representation both optimizes for egocentric viewing and minimizes inference time. Then we devise retina-matched perceptual models based on this representation. We consider both visual acuity and stereoscopic acuity to achieve high perceptual quality as well as low latency. Lastly, we derive an analytical spatial temporal model to optimize our method towards the balance of quality and latency. As a result, our method significantly improves responsiveness to about 50 fps while achieving the same perceptual fidelity as ground truth. Now we will dive deeper into the details of our method. Our egocentric neural representation depicts the rapidly varying first-person views with concentric spherical coordinates. The points are sampled at the intersections of rays and spheres. As egocentric viewing has little viewing changes but large spatial variance, we further design the network to infer concatenated vectors of samples per ray. The outputs are integrated via the volume rendering method. Our egocentric neural representation achieves significantly higher quality as well as faster rendering for egocentric viewing. However, when rendering the high resolution and stereo frames, it still suffers from a high latency of about half a second. To this end, we further leverage the spatially adaptive human visual and stereo sensitivities to unlock real-time inference. Inspired by previous work on geometric-based Foveated rendering, we synthesize three elemental images with decreasing angular resolution adapted to the visual acuity. We further devised two networks with different hyperparameters. The Foveated network has more capacity to enable high-fidelity rendering for the fovea, while the periphery network enables the faster rendering for the middle and the far periphery. A fast blending is then executed to generate the final frame. By adapting visual acuity, about 98% computational cost is saved compared to full resolution rendering by the Foveated network. Considering the stereo opposites, a naive approach that renders all elemental images for each eye will double the latency. Instead, we accomplish the inference with the adaptive stereoscopic accuracy. Psychophysical studies have revealed that human stereo opposites decline significantly with increasing eccentricity. Motivated by this, we assign the same elemental images to both eyes at middle or far periphery. This leads to no disparity outside the fovea, which is imperceptible to the viewer because of the low stereoscopic accuracy. Our adaptive stereo approach is 25% faster than naive stereo rendering. In our method, the quality and performance are affected by several hyperparameters. Enlarge these parameters could generally improve the quality but worsen the performance. While VR structure demands both quality and performance, to seek balance for human viewers, we present a spatial temporal model that analytically depicts the correlations and optimizes these parameters. With this model, the optimal hyperparameters could be determined through an optimization mechanism. Here we choose the quality and latency of various parameter settings. We show that the settings of best performance generate poor images which only capture approximate structure, while the settings of best quality generate high quality images with high latency. Our method balances both perceptual quality and latency. To evaluate the effectiveness of our approach, we conducted several subjective and objective studies. We first conducted a psychophysical study to investigate how users perceive our method compared with nerve and ground truth images. In the study, each trail consists of a pair of stimuli generated from two of the three conditions. The order of conditions among trails was randomized and counterbalanced. To avoid the gaze motion variance among individual trails, we enforced a static gaze in a trail, which was indicated by a green cross on the display. Once the participants focused on the green cross, the first stimuli appeared for half a second, followed by a 0.3 breaks to flush the version. Then the second stimuli also appeared for half a second. After each trail, the participants were asked which of the two stimuli had higher visual quality. Here are the votes from 20 participants. We observed close to random guess among our method and ground truth. Meanwhile, our method and ground truth both got a significantly higher ratio over nerve. The result shows the statistical perceptual similarity between our method and the ground truth. In addition to this, both conditions showed a significant quality preference over nerve. Next, we objectively validate the perceptual quality of individual eccentricities in a breakdown fashion. For each scene, we sampled 25 views with gazes at the center and evaluated the lift metric every 5 degrees. We compared our method, NeRF, and the traditional image space variation method, which serves as a spatially adaptive reference. Here we take the bubble shop scene as an example. The plot shows a significantly stronger perceptual similarity of our method compared to NeRF in the foreview. When extended to middle and far periphery, we observed a lower lift of our method compared to the traditional foveation method, which shows that our method does not compromise the peripheral vision quality. We further validated our method with free-headed gaze motion by evaluating subjective viewing trajectories with the objective perceptual metric for Foveated video. We collected 3 trajectories of poses and gazes for each scene from users viewing in VR. Each trajectory has about 100 frames. We compared the most recent FVVDP metric of our method, the traditional foveation method, and the recently presented ventral maximus method. Compared with the ventral maximus method and the traditional foveation method, our method has a significantly higher similarity, showing our outperformance in spatial temporal visual quality under dynamic viewing conditions. Finally, we visually compared our method with the recent panorama-based synthesis method. We observed a significantly higher quality of our method in scenes with higher occlusion and depth variance. We hypothesized that this is mainly because our approach presents better congruence toward learning complex geometry. In summary, we presented the first gaze constraint neural scene representation and a view synthesis method tailored for egocentric and stereoscopic VR viewing. We further derived an analytical model depicting quality-latency balance. Our approach enables high perceptual fidelity, low latency, and high-resolution VR viewing, and thus may serve as the first step towards future VR/AR systems that capture, teleport, and visualize remote environments in real time. Lastly, I will briefly discuss our limitations and the future work. Although our method unlocks a larger translation scale than panorama approaches, the optimal translation range is constrained by the radiance of the innermost sphere. Developing a corresponding network that synthesizes the imagery from global to local level of detail would be an interesting direction that extends the applicability to traversal scale translation and large scenes. Aliasing in the periphery exists because of the low sampling rate, while our studies have shown that aliasing doesn't cause significant degradation of perceptual quality. A candidate solution that applies multi-scale encoding, as proposed by Byron et al., can be investigated in the future to reduce the aliasing. Currently, we sample the scene fully based on eccentricity, considering acuity and stereoscopic. However, we imagine that fine-grained visual sensitivity, such as luminance or depth, would provide more insight into achieving higher quality and faster performance. Thank you.